Hey everyone, welcome back to another problem in our LeetCode 75 study plan series. So today we're moving on to a new category. We're doing binary BFS, and BFS stands for breadth first search. And if you don't know what breadth first search is, think of it as a method of traversing a tree or a graph, and we visit each node on each level first before going down to the next level. So if you're unfamiliar with breadth first search, then I will leave some resources in the description for you to learn more about that before you try tackling some problems yourself. But anyways, the name of the problem we're doing is called binary tree right side view. And the instructions are: given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. And so basically what our goal is here is to return rightmost the rightmost node on each level by performing a breadth first search. And so how we're going to achieve this in our implementation of this solution is primarily through using a queue and the breadth first search tactic or approach. So the first thing that we want to do is, since we're returning a list of integers, which is going to represent the values of the nodes, we're going to want to initialize that list. And we can call that list results. Sorry, my bad. All right, list of integers. I really can't type today. And then we're going to call this results. And then to initialize it, new, and then array list. All right, there we go. And then what we want to do real quick is just check for an edge case. So there is the possibility that we could be given an empty tree. So what we're going to want to do is, if the root is equal to null, then we're just going to return results. And this is going to be the newly initialized list, which is empty. And so we're basically just returning an empty list if the if root is null. All right. And then now what we want to do is, as I mentioned earlier, we're going to be using a queue. A queue is a data structure that adheres to the first in, first out principle. All right, so let's go ahead and initialize that data structure. So it's going to be a queue of tree nodes. So queue tree node, queue. And then in order to initialize this, it's going to be an implementation of the linked list data structure. So that's how we'll initialize it. And then now what we want to do is, before we use the breadth first search, we're going to want to add the root to the queue. So in order to do that, we're just going to do queue add root. Okay. Okay, so now let's set up a while loop, and this while loop is going to keep going while the queue is not empty. So while queue is empty, all right, and then we're going to add an exclamation point. So basically, it reads as while queue is not empty. And then we want to get an integer called size that's going to represent the size of the queue, and you'll see why in just a second. Okay, and then now what we're going to do is have a for loop inside of this while loop. So for int I equals 0, just our standard for loop. I is less than the size, I plus plus. All right. And basically what this is going to allow us to do is work on each essentially work on each level of the queue. And by level I mean like 1 and then 2 and 3 and then 5 and 4. So basically what we're going to do is, since the objective of this problem right here is to get the rightmost value. So you might be thinking as an initial solution for this problem that you would just want to add the very right node and just traverse down the right node. So 1, 3, 4, because that's what it says right here, right? But what if we have a case where this goes down another level? So 5 maybe goes down to 6 down here. We have to check the left side of the tree as well for the rightmost on that side, because if there's no more nodes after here, say in this case it just stops right here, but we still have a right node, a right child node for this left side, then we have to count that as the furthest right node. So it's not just the right side of the tree, it's the rightmost node of the entire tree, if that makes sense. So basically, we're going down each level and we're trying to see what the rightmost node of each level is. So hopefully that makes sense to you. All right, so inside of our for loop, we're going to want to pull, which means to get the top of the queue. So tree node and then tree node current equals queue the pull. All right, and then if I equals size minus 1. Remember, we're using size minus 1 because eraser 0 indexed. Okay, results dot add dot current dot value. Okay, so we're only adding the last node in the current value to the results list. All right, and then after this, we're going to have to add both the nodes of the left and the right side if they're not null. So if current dot left is not equal to null, then queue dot add current dot left. All right, and we're going to do this for the right side as well. Wow, I just really can't type today. All right, and then now what we want to do is after we're out of this while loop, we just want to return results. All right, let's run it, make sure we pass the first few. All right, it doesn't look like we actually passed the first few. Oh, it's because I put integers, not integer, just a simple typo. All right, so let's run this. Perfect. All right, and we'll submit. And we passed it. All right, so to analyze the time and space complexity, the time complexity is going to be big O of n. And that's because each node is processed once in the traversal. And then there are a total of n nodes in each binary tree. Thus, the breadth first search traversal will take linear time proportionate to the number of nodes, leading to a time complexity of big O of n. And then for the space complexity, we're going to say big O of w. And w is going to represent the width. So the maximum amount of space is used by the queue, which can hold all the nodes of the widest level, which is the breadth of the tree. But in the worst case, when the binary tree is a complete tree, which means that the bottom level can have n over 2 nodes, or half of n nodes, where n is the total number of nodes. However, because the number of nodes n can vary greatly depending on the shape and the height of the tree, we usually denote the space complexity in terms of w, the maximum width of the tree. Therefore, the space complexity of the breadth first search approach is big O of w. In the worst case scenario, however, for a perfectly balanced tree, w would be n over 2, making the space complexity big O of n. But in general, using big O of w gives us a clearer picture, as the width can be much less than n for skewed trees. All right, so I hope that you enjoyed this problem and that you learned something. If you did, please go ahead and leave a like for this video, and then also subscribe for more related content. We're still going to do every problem of this series, so stay tuned, and I'll see you in the next video.